Jai Hind everyone. Today I am going to discuss with you all the second class of pericyclic reaction, that is cyclo-addition reaction. Cyclo-addition reaction is like electrocyclic reaction is an important class of pericyclic reactions. The most famous example of cyclo-addition reaction is Diels-Alder reaction, in which dibutene add up with ethylene to form cyclohexene. This reaction is an example of cyclo-addition reaction and it is known as Diels-Alder reaction. So what are cyclo-addition reactions? Here we have two words, cyclo plus addition, means two unsaturated systems, two systems having pi electrons add to form a cyclo product. Here I have these two systems having pi electrons or pi bonds, and what we get ultimately a cyclic product. So here in this case, in reactant, I have 1, 2, 3 pi bond and 1, 2, 3, 4 sigma bonds, and in product side I have only one pi bond and 1, 2, 3, 4, 5, 6 sigma bond. So what we ultimately get, the loss of 2 pi bonds and gain of 2 sigma bonds. So here during cycloaddition reaction, 2 pi bonds get converted into 2 sigma bonds. What are cycloaddition reactions? So in simple language, cycloaddition reactions are those reactions in which a system having m number of pi electrons get add up with another system of having n pi electrons and we get a cyclic product. So simply these reactions are represented as m plus n plus systems. Here we may also have more than 2 pi electron systems, and in some cases the cycloaddition reactions also take place intramolecularly. So basically these are intermolecular reactions, but there are some examples where cycloaddition reaction take place within a particular molecule. So this is an example of cycloaddition reaction. Here let me share another example of cycloaddition reaction. Okay, here I have 2 ethylene molecules, right? And these 2 ethylene molecules convert into cyclobutane. This is another example of cycloaddition reaction. Like electrocyclic reactions, these reactions are also take place under either thermal or photochemical condition. Next example of cycloaddition reaction is a system having 2 pi bonds get add up with another system having only 1 pi bond. So here we will get this product. Okay, so as per this definition of cyclo-addition reaction. This is an example of 4 plus 2 cyclo-addition. 4 pi electron add up with 2 pi electrons. This is an example of 2 plus 2 pi electron system, and this example is 2 plus 2 plus 2. Okay, these 2 electrons take part in cyclo-addition reaction. These also take part, and here we have the third set of pi electron. So 2 plus 2 plus 2. It is an example of 2 plus 2 plus 2 cyclo-addition reaction. So here I have shared some examples of cyclo-addition reactions. Cyclo-addition reactions are those reactions in which 2 or more than 2, and in some cases only one system, form cyclic product by the conversion of 2 pi bonds into 2 sigma bonds. Okay. Okay, so in cyclo-addition reactions, the addition of 2 systems yield a cyclic product, and this addition take place either on the same phase or on opposite phase. So if the addition take place on same phase, then it is termed as suprafacial. Okay, let me explain this with the help of this particular example. Suppose the addition take place like this, then it is from the same phase, or like this, then this addition is also from the same phase. So this type of addition is termed as suprafacial addition. So stereochemically, two type of addition take place, supra or entera. Now you must have guessed about the second type of addition. Second type of addition is called intra-addition. Intra-addition means one sigma bond will add from, for example, one sigma bond form on the upper hand side and another will be formed from the lower face. So here these two bonds formed on opposite faces or opposite sides. So this type of addition is termed as entera or intrafacial addition. Okay. It is intra and this one is suprafacial. So two stereochemical mode of addition are possible, supra or intra. Okay, now let me explain this with the help of some pi orbitals. Okay, first, so basically on the basis of these two type of stereochemical additions, there are 4 conditions. Supra number 1, number 2 intra, number 3 supra intra, or number 4 intra supra addition. So what are these additions? Let me explain with the help of these examples, these diagrams. Okay, suppose here I want to add this system of 2 pi electrons with this another system of 2 pi electrons. So if the addition takes place like this, from upper lobe to upper lobe or lower lobe to lower lobe, then this type of system is termed as supra addition. And if it is like this, upper to lower or lower to upper low, then this type of addition is termed as intra addition. Next type is supra intra addition. What is supra intra addition? Supra means same, upper or lower, right? And intra means one upper another lower, or one lower another upper. So this type of addition is termed as supra intra. Similarly, another type of addition is also possible, intra supra means upper low with lower low, and supra means upper with upper. Similarly, we can also construct another type of diagram. So I hope you understand these terms, supra intra, supra intra or intra supra type of addition. If supra is given, means addition of the two systems is from the same side, or especially from the two similarly oriented orbitals. Here in this case, upper orbitals, if take part in addition, then this is termed as supra, or lower, then this is also termed as supra. But if one upper orbital, another lower orbital take part in addition reaction, then this type of addition is termed as intra addition. Okay, so basically four type of addition are possible: supra, intra, supra, or intra supra type of addition. So cyclo-addition reactions can be classified on the basis of these three factors. What are these three factors? Number one is the number of electrons of each unit participating in cyclo-addition reaction. How many electrons are participating? Number two, the types of orbitals undergoing the change, whether these orbitals are pi or sigma. And number three is the stereochemical mode of cyclo-addition reactions. It is supra or intra. So we can understand this process with the help of one example. Let me explain this by taking the example of Diels-Alder reaction. Okay, so here I have ethylene. Let me write it as S. So it is an example of 4 plus 2 cyclo-addition reaction. Okay, and in this cyclo-addition reaction, pi orbitals are taking part. So here we have two conditions. The parameters that we use to classify cyclo-addition reactions. Here we have two parameters. That is type of the electrons or orbitals. Here pi orbitals are participating in the cyclo-addition reaction, and number two is the number of electrons. Number of electrons for first unit is 4 and for second unit is 2. So basically it is 4 plus 2 cyclo-addition reaction. Okay, now we may have four type of situation here. So first is the supra addition, right? Let me write here. It is supra addition. So after addition, I will get cyclohexene Okay, this arrow tell us that this R will go away from the viewer. Okay, and this arrow in downward direction. If arrow is in upward direction, then this it means the group will move away from the viewer, and if arrow is in downward direction, then the group will move towards the viewer. Okay, so here these two X will be oriented towards me, and these two R will go away from me. So how will I represent this particular reaction? This reaction is an example of 2 pi electron system with 4 pi electron system. Both are taking part from the same phase, so it is pi 2 supra plus pi 4 supra cyclo-addition reaction. Okay, here the addition is from same side, right? So we will get this particular product. Start. Okay, so next is intra-supra-addition. Intra-supra-addition. Here I have R, H, okay, so it is intra-supra-addition. So this particular group will go away from me and it will come towards me. Similarly, it is supra, so I will write this like this, and the product will be a cyclohexene having 2 R in oriented opposite to each other. It is towards me. Okay, so this is an example of intra-supra-addition. Okay, let me convert this into supra-intra. So how will I represent this addition? It will be represented as pi 2 supra plus pi 4 intra-addition. Okay, let me convert this particular into supra intra-addition. So I will change the direction of this arrow. Right now it will be arranged like this. So it is an example of pi 2 intra plus pi 4 supra addition. Similarly, we can also write the intra-intra addition. In intra-intra addition, both the groups, both the R and X will be oriented opposite to each other. Let me write directly. I will write the product here. So it is our reactant. Okay, now what I am doing, I am performing intra-addition. So it is R, H, X, and X. So intra means one in upward direction, another in downward direction, similarly it is in downward direction, it is in upward direction. So what will be the product? Product will be a cyclohexene having both the groups oriented opposite to each other. So this, it is in upward direction, it means it is going away from me, and this particular is coming towards me. Similarly, it is, this X is coming towards me, and this particular another X is going away from me. So both the R are oriented opposite to each other. Similarly, X are also oriented opposite to each other. So it is an example of pi 2 intra plus pi 4 intra addition. So here I have explained all the 4 type of addition that include the 3 parameters. What are these 3 parameters? These 3 parameters are the number of pi electrons participating in the reaction, number 2 the type of orbital that is going through the change, and number 3 is the stereochemical mode of cycloaddition, whether it is supra-supra addition or supra-intra or intra-intra or intra-supra addition. Okay. Okay, let me share some examples of cycloaddition reaction. So okay, this reactant take part in addition, and we get 2 type of product. One is head to tail cycloaddition, okay, it is head to tail addition, and another is head to head cycloaddition. It is head to head cycloaddition. So it is an example of 2 plus 2 pi 2s pi 2s or pi 2a pi 2a, means supra-supra or intra-intra cycloaddition take place in this particular example. Similarly, here I have another system. Okay, this system have 6 pi electrons. It is cycloheptatriene, and it form cycloaddition with this it is cyclopentadienone. Okay, it is a 4 pi electron system, right? So actually it is pi 6s plus pi 4s cycloaddition reaction. So this group will move, pi electrons will move like this. Okay, and we will get the product like this. It is our CS2 unit. Here Okay, so this is product of result of pi 6s plus pi 4s cyclo-addition reaction. Similarly, the example we already discussed is an example of it is Cn, it is also Cn. So it is an example of pi 2s plus pi 2s plus pi 2s cyclo-addition reaction. So here we have these three examples of cyclo-addition reaction in which I tried to mention both the number of pi electrons as well as the stereochemical aspect of this cyclo-addition reaction. Okay, so we have discussed three examples of cyclo-addition reaction in which two reactants take part. Here I am sharing another example of cyclo-addition reaction having only one reactant. So here we have two R groups. Let me write it R1 and this one is as R2. Okay, so in this reaction it is an example of 4 plus 2 cyclo-addition reaction. Here the movement of pi electrons will be like this. Okay, and this will move towards this particular carbon. So after the cyclo-addition, it is thermal process. This particular carbon is taking part in the formation of a sigma bond with this particular carbon, right? So the movement of this R will be towards viewer and H will move away from us. No, it is like this. This R2 will move away from me and R1 will move towards me. Similarly, this carbon will form a bond, sigma bond with this particular carbon. So here it is cyclopropane system having R1 towards me and H away from me. So this is an example of intramolecular cyclo-addition reaction. Here we have only one reactant. Okay, so remember this particular example. It may also be written like this. Let me write this 1, 2, 3, 4, 5, 6. Okay, so this 6, 5, 4, 3, 2, 1. So we have one double bond between carbon number 2 and 3 and have R2 here. Now after complete rotation, this R2 will come towards me and R1 will go away from me. So this may be written like this. Okay, so it is an example of intramolecular cyclo-addition reaction in which 4 plus 2 pi 2 intra plus pi 4 supra addition take place. Okay, because of this, the movement of, actually it is intrafacial, so the orientation of both the R will be opposite to each other. So you may also choose the correct option by observing the orientation of these two arcs. If in the option both these are oriented in opposite direction, then that particular option will be correct. Okay. So after discussing the general properties of cyclo-addition reaction and some of the example of cyclo-addition reaction, now we will discuss about the three approaches to explain the cyclo-addition reactions. So first one is correlation diagrams. Okay, so molecular orbital symmetry in cyclo-addition reaction, how the symmetry of molecular orbitals affect the cyclo-addition reactions, we will try to understand with the help of the simplest example of cyclo-addition reaction, that is 2 plus 2 cyclo-addition reaction, or addition of 2 ethylene to form the cyclobutane. Okay, here while discussing the correlation diagrams, we consider two type of plane of symmetry, horizontal and vertical plane of symmetry. So here let me write these two symmetries. Suppose it is the orientation of hydrogen in these two molecules is like this. Okay, so you can see that here we have 4 CH2 units in this cyclobutane if there is no substituent present. So this particular symmetry is sigma H. It is horizontal plane of symmetry, and similarly we have another plane of symmetry. It is termed as sigma V, or vertical plane of symmetry. Vertical plane of symmetry. So in this case, let me check. You can see these two H are situated like this. These are above the plane of this board, and these two are below the plane of board. So here we have two similar ethylene without any substituent. So these two can be bisect by taking this particular plane. Okay, so both these have sigma H as well as sigma V, right? But we also consider the product, whether this product have both the symmetry properties, that is sigma H or sigma V, or not. So luckily both the reactant as well as product have both type of plane of symmetry, horizontal as well as vertical plane of symmetry. Okay, so we will discuss about these two symmetry elements in the orbitals of the reactants as well as the orbitals of the product, and then we will check the symmetry properties of the orbital of reactant with match the symmetry properties of reactant with the symmetry properties of the product. If they are matching, then we will conclude whether this process is thermally allowed or photochemically allowed. So here we have two pi bonds. So you know that in the formation of one pi bond there are two orbitals take part. So we have 4 pi orbitals, right? These 4 pi orbitals take part in the formation of the molecular orbitals. So here I have 2 pi orbitals. These 2 orbitals will form pi 1 and pi 2. These are 2 bonding orbitals. Similarly, I will also get pi 3 and pi 4. Okay, these are anti-bonding molecular orbitals, right? So 4 atomic orbitals will form 4 molecular orbitals, and you know that when atomic orbitals take part to form molecular orbitals, then we will get equal number of molecular orbitals. If n number of orbitals taking part, n number of atomic orbitals are taking part in the formation of molecular orbitals, then we will get equal number, means n molecular orbitals, half of which will be bonding and another will be anti-bonding. Bonding means the molecular orbitals have less energy as compared to the atomic orbitals, and anti-bonding molecular orbitals means orbitals have more energy as compared to the atomic orbitals. So these 2 bonding orbitals, pi 1 and pi 2, are bonding orbitals, and pi 3 and pi 4 are anti-bonding orbitals. Okay, similarly, sigma orbitals will also take part to form sigma bonding and sigma anti-bonding orbitals. So we have to draw correlation diagrams for these pi as well as sigma orbitals. Let me write here the orbitals for both reactant as well as the product. Okay, so first I will write the orbital for the ethyl. Okay, so simplest example of the cyclo-addition reaction is 2 plus 2 cyclo-addition. Here 2 pi bonds take part in cyclo-addition and form 2 new sigma bonds. Okay, so we will first discuss the symmetry properties of the reactant orbitals and then the product orbitals. So here let me write the properties of these reactant orbitals. So here we will discuss about 2 types of symmetry properties. One is sigma V and another is sigma H. Okay, so we have 4 pi molecular orbitals. Out of these 2 are bonding and another 2 are anti-bonding. So first orbitals are without any lobe. So it is symmetric with respect to sigma V and also symmetric with respect to sigma H. So it is our sigma V. Okay, you can see on both the sides, left hand side and right hand side, we have same sign, that is minus minus or plus plus. Similarly, if I apply this horizontal plane, then I will also get 2 identical situation, plus plus minus minus. Okay, next one is plus plus minus plus. Okay, so it is symmetric with respect to sigma V and asymmetric with respect to sigma h. Okay, if I apply sigma s, then I will get plus sign on upper hand side and minus sign on lower hand side, lower side. So it is asymmetric with respect to sigma h. Similarly, it is plus minus minus plus plus minus plus minus. It is asymmetric with respect to sigma v and symmetric with respect to sigma h. Okay, sigma v, if I apply sigma v, plus plus minus 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 plus plus, and here if I apply sigma h, then I will get the opposite orientation. And next one is the asymmetric orientation. Okay, so it is asymmetric. So these are the symmetry properties of reactant orbitals with respect to these two symmetry elements, that is vertical and horizontal plane of symmetry. It is psi 1 square, it is psi 2 square, psi 3 square and psi 4 square. Similarly, I will write the symmetry properties of the product. Okay, actually it is ethylene to cyclobutane conversion. So here I will write the orbitals of the product. I will also inspect the same symmetry properties, sigma h and sigma v, right? Let me write here sigma v and here sigma h. This third, orbitals fourth. Okay, it is sigma 1 square, sigma 2 square, sigma 3 square and it is sigma 4 square, right? So first is plus plus minus minus. So it is sigma v and sigma h. Okay, so this particular set of orbital is symmetric with respect to vertical plane as well as it is also symmetric with respect to the horizontal plane. So symmetric. Now here in this case I have sigma 2 square plus minus plus minus plus minus minus plus. So it is symmetric with respect to sigma h and asymmetric with respect to sigma v. Okay, you can also apply this particular vertical plane. After applying this plane, you will get plus sign on your left hand side and minus sign on your right hand side. So it is asymmetric with respect to sigma v. Next is here I have plus plus minus minus. So it is asymmetric with respect to sigma h and symmetric with respect to sigma v. And next one is plus minus plus minus minus plus minus plus. Okay, it is asymmetric with respect to both sigma v and sigma h. Okay, so here I have constructed the molecular orbitals for both reactant and product and also mentioned the symmetry properties of all the molecular orbitals both with respect to both the symmetry elements sigma v, that is vertical plane of symmetry, as well as sigma h, that is horizontal plane of symmetry. Now let me draw the correlation diagram for both these products. So here on this side, on my left hand side, I will write the symmetry properties of the reactants. So sigma V, sigma H. We will write these properties in the same sequence. So it is SS, SA, AS and AA. Here on right hand side I will write the symmetry properties of the product, or sigma 1, sigma 2, sigma 3 and sigma 4. So it is sigma B, sigma H. Symmetric, symmetric, asymmetric, symmetric, symmetric, asymmetric, asymmetric, asymmetric. Okay, these are the symmetric properties of sigma V, sigma H. Okay, now here it is the non-bonding line. So now you can correlate the reactant orbitals with the product orbitals by taking in mind the symmetry properties. So here psi 1 square will be correlated with sigma 1. Okay, both are symmetric SS. Here psi 2 square is SA, but sigma 2 is AS. So it can be correlated with, cannot be correlated with this sigma 2. Psi 2 cannot be correlated with sigma 2. And here we have the same symmetry properties of this. Sorry, it is SA. You can see it is SA. So it can be correlated with psi 2 can be correlated with sigma 3 and psi 3 correlate with sigma 2 and psi 4 correlating with sigma 4. So you can see that the non-bonding line get crossed while matching the symmetry properties of reactant with those of the symmetry properties of reactants. I may also write the electronic configuration of the reactant orbitals with matching with these with the product orbitals. So psi 1 square, psi 2 square get converted into from sigma 1 to sigma 2, sorry, sigma 3 2. Okay, so you can see to get this particular configuration we have to cross the non-bonding line. So in thermal condition this process is not possible, right? But if I apply photochemical condition, in photochemical condition one electron will get promoted from psi 2 to psi 3. Now this psi 3 correlate with sigma 2 and psi 2 correlate with sigma 3. So in the photochemical condition the electronic configuration will be like this: psi 1 square, psi 2 1, psi 3 1, and we will get the electronic configuration like this: sigma 1, sigma 2 and sigma 3. It is anti-bonding. Likewise this. So this photochemical condition for this particular 2+2 cyclo-addition is symmetry allowed process, but the thermal process is symmetry forbidden process. I hope you may understand the correlation diagram for this particular example of 2+2 cyclo-addition. Okay, now let me share another example of correlation diagram, that is 4+2 cyclo-addition reaction. 4+2 cyclo-addition reaction. Here in 4+2 cyclo-addition reaction, one diene add with dienophile to form cyclohexene. Okay, now if you try to apply the two symmetry elements, that is vertical plane of symmetry and horizontal plane of symmetry, then you will find that here we have only one plane of symmetry, that is sigma V. Here sigma H is absent in this particular case. So we will study this particular example with the help of these two symmetry, these only symmetry property, that is vertical plane of symmetry. Okay, it is addition reaction of butadiene with dienophile. So here on left hand side I will write the symmetry properties of reactant, or on right hand side I will write the symmetry properties of product orbitals. So here first one is diene, okay, so it is Psi1, then I have dienophile, it is pi, then another diene, Psi2, here I have Psi3, and pi2, then Psi4 plus minus plus minus plus minus plus minus. This Psi1 have 0 node, 0 node, 1, 2, 1 and 3 node. Okay, so we will keep in mind only one symmetry element, that is sigma V. So it is symmetric with respect to sigma V. Okay, similarly it is also symmetric, it is asymmetric, symmetric, asymmetric, and then we have last one is also asymmetric with respect to sigma V. On the right hand side I will draw the orbitals of the product. Okay, so here one sigma bond will be formed by the overlapping of the orbitals of the same side. Okay, next one is please keep in mind that in product we will get two extra sigma bonds as compared to the reactant. Okay, so here it is another minus minus plus plus. Okay, next one is pi orbital. So here I will mention this orbital in this way. This is our non-bonding orbital line. Next is another pi orbital, plus minus plus minus. Okay, it is sigma 1, sigma 2, pi 1, pi 2, then I have next is plus minus, sorry, it is minus plus, it is plus minus minus plus. Okay, and here I will have, okay, actually it is minus, it is plus, plus, then minus, and last one is also like this, plus minus plus minus, it is plus minus plus minus. So you can see it is this first orbital, sigma 1 is symmetric with respect to horizontal plane. Okay, here it is asymmetric, it is symmetric, it is asymmetric, symmetric, and last one is also asymmetric, right? So now draw the correlation. Okay, now after writing the symmetry properties, I will correlate the orbitals of the reactant with the orbitals of the product. So both psi 1 and sigma 1 are symmetric with respect to sigma v. Similarly, pi is symmetric but sigma 2 is asymmetric. So I will correlate with pi 1 and this psi 2 with sigma 2. Similarly, it will correlate with this, and these two will get correlate with each other. So here, after observing this correlation diagram, I can write the electronic configuration, this particular example, like sigma 1 square pi 1 square sigma 2 square get converted into sigma 1 square, sigma 2 square, and pi 1 square. So this process is thermally allowed process. Okay, 4 plus 2 cyclo-addition is thermally allowed process. Why thermally allowed process? Because we do not need to cross the non-bonding line to match the symmetry properties of the orbitals of reactant with the orbitals of the products. Okay, so this process is symmetry allowed and it is thermally allowed process. So if I will try to check whether this process is photochemically allowed or not, then I have to promote one electron from psi 2 to psi 3. Then what I get that this particular psi 3 will match with this sigma 3 and it is sigma 4, right? Then the configuration will be psi 1 square, pi 1 square, psi 2 1, psi 3 1, and here on the other hand side I will get psi 1 square, psi 2 square, and pi 1 square. So the matching does not take place. So 4 plus 2 cyclo-addition reaction is thermally allowed process. I hope you understand the correlation diagram with respect to the cyclo-addition reactions. Still, if you have any doubt, then please do not hesitate to ask your doubts. Thank you, students. Thank you very much. Jai Hind, Jai Bharat.